Namaste, greetings of the day. I am Dr. Vamsi, working as an assistant professor in the Department of CSE AI. Today in this lecture, we'll see a concept called coding of our neurons in artificial neural networks. This concept comes under unit number 3, deep learning subject, which is available in third year, second semester. Generally comes to the artificial neural network. It contains 3 layers. First one is input layer, second one is hidden layer, a group of hidden layers. Third one is output layer. In the machine learning, we are giving the dataset as an input to the model. The dataset contains a sequence of features or lots of features. So these features are fed to the model through input layer. With the help of hidden layer, these features fed to the input layer are extracted with the help of random weights. So today we'll see how the model can understand the weighted sum with respect to the inputs. Depends upon your problem statement, the number of neurons you are taking in the output layer for regarding binary classification, for regarding multi-class classification. So generally, the artificial neural networks is a combination of these 3: input layer, hidden layer, and output layer to process the model output. Coming to the today's lecture flow, introduction of a neuron, structure of artificial neuron, different cases for construction of neurons with layers of neurons, with vectorization, nothing but NumPy implementation, and batch processing of data through NumPy. So let us have discussion on what is a neuron. So neuron is a function that gives some output value. So this output value is usually very small, in between 0 and 1. So here I'm going to show you a simple single neuron which accepts input feature as input and produces an output after processing it. If you observe here, this neuron is going to have a function. Technically, we are calling it as activation function, which decides whether to activate a neuron or not to send the signal to the output layer or to the coming hidden layers. Now, let us understand the architecture of artificial neuron. So the artificial neuron is also called as perceptron, which contains 2 components. First component, as you see here, it is a weighted sum. Weighted sum is nothing but sum of product of weight matrix with input vector. And the second part, if you observe here, is f of z. So how to calculate z? Z value will be calculated with the help of the result of first part, wi into xi, with summation on all the inputs vectors and the weighted matrix. On that result, we are going to apply an activation function. So we'll see different types of activation functions in the coming lectures. So today's lecture will see how to calculate the weighted sum in different case studies with vectorization or in a form of scratch program, nothing but without using NumPy. So if you observe this neuron, the first part will be enabled first. The result of first part is given to the second part so that the output will be given. So if you observe the flow of the structure of artificial neuron, this neuron will take different input features. Here the given as x1, x2 and so on xn. So these input values are multiplied with weight matrix denoted as w1, w2 and so on wn. So once the wi xi is ready in the form of summation, then the result will be given to the activation function so that you will get the output. Okay, so if you observe what is the mathematical equation for this first part, so how to calculate the z is, it is nothing but the weight of first feature of weight matrix and the first input feature plus W2 into X2 and so on up to Wn X. So if you calculate this equation, you will get the Z value. On the Z value, you are applying the activation function. Here, the activation function, it is denoted as f of z, and it is represented as the term y. So here, depends upon the y value, we are going to be define the constraints. So let us discuss one sample constraint. So if f of z is 1, ultimately you are activating the neuron, which represents a binary 1. And if f of z is 0, which represents a binary 0, so this can be given if the z value is less than or equal to 0. So if you observe, this f of z can be 1, can be 0, can be determined from the probability value in between 0 and 1. So as per the discussion, we can identify this neuron will give usually a small output value in between 0 and 1. So once the y gets the probability value, on that you are applying these constraints to find out whether the neuron can be able to get the signal or not. So this type of neurons, you can take it as an application for cat versus dog. So if the f of z is 1, I can take it as my input features belongs to cat, otherwise the input features belonging to dog. Now let us discuss about different case studies for constructing the neurons, group of neurons, vectorization, without vectorization. So let us discuss about a simple, the starting case, nothing but single neuron. So as the name suggests, it is a single neuron. It takes the input values from the input vector, weight values from the weight vector, and the bias value. So here bias value is only 1 because we are taking single neuron. So if you observe the architecture of this, so here the neuron I have taken can be calculated by using W nothing but weight multiplication of input vector nothing but x plus bias, which represents my final output. If you observe the input flow of this neuron, so here I have taken the input vector with dimension 1 by 4 and the weights dimension also 1 by 4. So inputs vector contains the values are 1.0, 2.0, 3.0 and 2.5. These inputs are fed to the single neuron along with weights. So the weights are taken from the weight vector. The values are 0.2, 0.8, minus 0.5, 0.3. So these values will be given to this neuron, so that you are applying the multiplication between every value from the input vector and the weight vector, so that the final answer of w into x will be summed with bias. The bias value is 2.0. If you observe the tracing of this neuron, so it is nothing but w into x, 1 into 0 into 1.0 into 0.2 plus 2.0 into 0.8 plus 3.0 into minus 0.5 plus 2.5 into 0.3, and on that result you are adding the bias, so finally you will get the output as 3.5. So let us see the remaining examples. So under case number 2, here I am trying to take 4 input values, nothing but input vector, and 3 neurons. So 3 neurons, I am going to be take 3 separate weight vectors. First neuron takes weights 1, second neuron takes weights 2, third neuron takes weights 3, but for all these 3 neurons my input data is common. So let us see how the architecture will be framed, so that you can understand the tracing, how to construct this case to represent 3 neurons with 4 inputs. So let us have discussion on how to construct neuron 1, which takes input data with weights 1 plus bias of index 0. So here if you observe the bias, also a vector which contains 3 elements, so that bias index 0, neuron 1 takes, bias index 1, second neuron takes, bias index 2, third neuron takes. So let us go for the tracing. So like previously, here also the formula is weights into input plus bias. So let us take the inputs, contains 4 values, 1.0, 2.0, 3.0, 2.5. So on neuron 1, I will take weights 1 vector with a dimension of 1 by 4 again. So that the values are 0.2, 0.8, minus 0.5, 1.0. So on this neuron 1, I will apply the W into X along with bias, so that I will get the output as 4.8. So this is called as neuron 1. Now let us go for the neuron 2 construction. This neuron 2 also takes same input values, but the weights values are from weight 2 vector. So this second neuron will take the input values like previously, and the weights from weights 2 vector, nothing but 0.5, minus 0.91, 0.26, minus 0.5. So on this input vector and the weights 2 vector, you're applying the mathematical weighted sum equation along with bias index 1 and the value is 3.0. So that you will get the final output as shown here. This is like tracing only. You will get the final value as 1.21. Now let us discuss about the neuron 3. So neuron 3 will takes the same input values, but the weight vector is from weights 3. So the weights values from weight 3 vector are minus 0.26, minus 0.27, 0.17, 0.8. These on these input vector and weight 3 vector, the weighted sum will be calculated along with the third element from the bias, nothing but bias index 2, so that we will get the final output as 2.385. So if you observe here, as of now, we have seen input with weights 1, nothing but neuron 1, inputs with weights 2, nothing but neuron 2, inputs with weights 3, nothing but neuron 3. So if you combine these 3 neurons together, the final architecture will look like this. So if you observe, every input value is associated to the every neuron that is available here, nothing but neuron 1, neuron 2, neuron 3, which represents a fully connected architecture. So why fully connected architecture means every data that is available in the input layer is connected to the every neuron in the next layers. So every neuron is having a specific bias values, so that every neuron will produce its own output values. So 3 outputs you will get according to this case. Nothing but 4.8 from neuron 1, 1.21 from neuron 2, and 2.385 from neuron 3. So in this by after this we'll discuss about some more cases, so that we can have the architectures on vectorization, adding of layers, and the batch processing. Now case 3, so which represents the same single neuron, how it can be implemented through vectorization. So vectorization is nothing but using a predefined libraries through NumPy, so that the NumPy will hide all these manual tracings. So the simply how to import the NumPy, and using some predefined libraries and the predefined functions, automatically in the background your NumPy will able to calculate the weighted sum along with addition of bias. So if you observe the same example we have seen previously, the input contains the dimension 1 by 4, the weights contains the dimension 1 by 4, and the bias is a scalar. So if you observe the vectorization representation on this example, so here you have to import the NumPy package with aliasing name np. So in this NumPy package, you are having a predefined method called dot, so that weights comma input plus bias directly you can take. So if you observe here, this dot method will take 2 parameters, weights comma input. The weights dimension is 1 by 4, and the inputs dimension is also 1 by 4. So vector with vector, so that no transpose is required. So this input values are will be taken, and the weights values will be taken along with bias. So here the red color is the manual tracing we have done previously. Now this tracing you no need to do, the vectorization method will take care if the dimensions are properly taken. So same value will be there. Now coming to the case number 4, layers of neurons. So previously under case number 2, I have taken input as vector, weights, 3 weights I have taken, those are also vector. So let us combine these weights in a form of matrix representation so that we'll have the dimension as row by column. So whenever you're applying a dot method which is available in the NumPy on inputs and weights, you have to satisfy the rule to proceed with the product on these two inputs and weights by applying the transpose. So here the dimension of input is 1 by 4 because it is a vector, and I'm combined all the individual weights in the form of matrix representation, and the dimension of this weights is 3 by 4. So if I try to apply the product on these inputs and weights directly, it can't be possible because to perform multiplication operation, the column of input and the row of weights should match. But here the column of input is 4 and the row of the weight is 3. So these values are not same, so that you can't apply product directly. So for that purpose, you have to apply the transpose on weights so that the weight dimension is 3 by 4 will becomes 4 by 3. So input dimension is 1 by 4. So 1 by 4 will be mapped with 4 by 3. So the final output will becomes the vector with the dimension 1 by 3. So if you observe after applying the transpose on weights, so 3 by 4 dimension becomes 4 by 3. So everyone knows the rule to perform a transpose, nothing but interchanging the rows and columns. So here the weight contains 3 columns if you observe here, and 4 rows. So that's why it is 4 by 3. So this can be represented by a variable called weights, a superscript of capital T, which represents on input on the given example of weights you applied the transpose operation. So now the product on 1 by 4 and weights transpose with a dimension 4 by 3 is possible. So if you apply product on this, let us go for the tracing. So the dot product will represent with a weighted sum, nothing but input into weights transpose, so that every input value will takes every column from the weights transpose. So that the equation will look like the input vector contains already 1.0, 2.0, 3.0 and 2.5. The dimension is 1 by 4, and this product in a combination of input data will be applied on every column from the weights transpose matrix. So nothing but the first column vector is 0.2, 0.8, minus 0.5 and 1. Second column vector contains weights 0.5 minus 0.91, 0.26 minus 0.5. And the third vector column contains values minus 0.26, minus 0.27, 0.17, 0.87. So these calculations can be done individually to fill every element that belongs to the output answer. So after performing the mathematical calculations, the first element which is available in the in between input to the first column of the vector is 2.8. The second element answer is minus 1.79, and the third element answer is 1.885. Along with the bias you have to take, so that the final answer is 4.8, 1.21, 2.385, which contains the dimension again 1 by 3. Now let us understand the same example through vectorization. So whenever you see the vectorization, you're trying to take the library's help. The best example, the best useful thing is NumPy. It is having a dot product, but you can't apply dot product directly because input is a vector, weight is a matrix. So that you have to apply, before processing it, you have to apply transpose on weights matrix, so that 3 by 4 becomes 4 by 3. So 1 by 4 into 4 by 3 is possible. So if you observe the vectorization representation after importing the NumPy, so you are taking weights dot t. Dot t represents you are applying transpose on weights, so that 3 by 4 becomes 4 by 3, comma input plus bias. So it takes every element, every row element from the weights vector, so that on that it is applying the transpose. The final answer is the same like your previous manual tracing. So now coming to the differences between vectorization and non-vectorization is, if the architecture is simple, it is easy to go for manual tracing. So what happens if the network is a complex network and the dimension is very high in terms of 2000 rows into 15 features? So it is very difficult for go for the manual tracing, so that you will take the help of vectorization. With the help of these predefined libraries, you can easily process the data. It can be used for data pre-processing stage. Now, coming to the case number 6, which represents layers of neurons and the batch processing data through NumPy. So, if you observe the previous examples, in all the previous examples I have taken input as still vector. Now, coming to this case, input also a big dimension, nothing but matrix dimension 3 by 4, and the weights also the matrix representation 3 by 4. So, if I want to apply dot product on 3 by 4 with 3 by 4, which represents inputs and weights, direct product is not possible because the column of input and the row of weights are not same. So that I have to apply the transpose on weights. If you observe, this is the main representation coming to the numpy dot dot inputs comma, and you have to treat this weight matrix with array representation. On that you have to apply the transpose. So that here if you observe, the color notation shows the input also having batches of data. So it is required to make the input data in form of batches and the weight matrix in the form of weights. So if you observe, the first row that is available in the input 1.0, 2.0, 3.0, 2.5 comes under batch 1. 2.0, 5.0, minus 1.0, 2.0 comes under batch 2. Minus 1.5, 2.7, 3.3, minus 0.8 comes under batch 3. So these three batches will be applied on every neuron that is belonging to the weight matrix, which represents, first column represents neuron 1, weights 1. Second column vector of this weights transpose represents neuron 2, weights 2. And the next one is neuron 3, weights 3. So now every batch will be every batch data will be given to every weights neuron. Let us observe this the complex type of architecture compared to the previous things. Now if you observe the batch 1 contains data here 1.0, 2.0, 3.0 and 2.5. This data is given to the all the three neurons, which represents three weights vectors of weights dot transpose matrix. So if you observe this architecture, so entire data 1.0, 2.0, 3.0, 2.5 are given to the every neuron that is available in this weight matrix, which is represents a fully connected neural network. So every neuron will have its own weights vector. So neuron 1 will have the first column vector, neuron 2 will have the second column vector, the neuron 3 will have the third column vector. So that three neurons are there, you will get three individual outputs for after processing this batch 1. So likewise you have to follow for batch 2 data and batch 3 data, because our network able to handle batch processing now through NumPy. Now let us see the batch 2. So the neurons structure with coming to the weights matrix is same and the input data is changing. So under batch number 2, the data input data is 2.0, 5.0, minus 1.0, 2.0, and the weight matrix contains the individual vectors are same, so that you will get another three outputs, nothing but 6.9 minus 4.81 minus 0.3, and these can be calculated like we have seen previously how to perform weighted sum w into xi plus b, nothing but bias. Now coming to the batch number 3, which contains data minus 1.5, 2.7, 3.3, minus 0.8. This information is applied on every neuron which is available in this network for every column vector. So the outputs are, after processing the weighted sum, the outputs are first neuron produces minus 0.59, second neuron produces minus 1.949, the third neuron produces output as minus 0.474. So likewise, if you combine three cases in terms of three batches on every neuron of weight matrix, this is the flow of tracing how to construct this complex architecture. So if you observe this architecture, every data from batch 1, every data from batch 2, every data from batch 3 is connected to the neuron 1, which is represents batch 1 weight 1 vector, batch 2 weight 1 vector, batch 3 weight 1 vector. So if you observe the second one, so here every data of batch 1, batch 2, batch 3 are connected to the second neuron, which represents batch 1 with second weight vector, batch 2 with second weight vector, batch 3 with second weight vector, all are connected to the second neuron. So coming to the third neuron, this is the flow. Every data that is available in the batch 1, batch 2, batch 3 are connected to the third neuron, which represents batch 1 weight 3, batch 2 weight 3, batch 3 weight 3. So if you combine the entire flow, this is the fully connected final architecture of case number 6. Input contains batches of data, a weight matrix contains different vectors. So that if you observe every data of batch 1, batch 2, batch 3 are connected to the respective weight vectors can be represented as neuron 1, neuron 2, neuron 3. So neuron 1 will get, like I have seen previously, the data from batch 1, batch 2, batch 3 on first column vector of weight matrix. So second neuron also will produce as output batch 1, batch 2, batch 3 with second column vector of weight matrix. Third neuron also will produce an output batch 1, batch 2, batch 3 with the third column vector of your weights matrix. So likewise, this is the final fully connected architecture which represents the case number 6, batch processing. So let us go for the next cases. So before going to the next cases, this is the flow. So generally, according to the previous discussion, every neural network will contains a group of layers, input layer followed by hidden layer followed by output layer. So generally, being a student, we're always focusing on how to initialize input layer, how to process or extract the important features in the hidden layer, and how the processed information given to the output layer. So if you observe, this is the final architecture of case 6. This entire manual tracing are hidden by your Python programming with the help of vectorization. So generally, being a student, you're writing the input layers, hidden group of hidden layers, and the output layer, right? So the background of construction of this input layer, hidden layers, and output layer is this. So this batch representation, which represents which are connected to the every column vector of weights are hidden to the user who are using the vectorization. So being a student, you should understand how in a background the batch processing is happening to construct the layers to frame artificial neural network. So if you observe here, here I am taking every batch contains 4 values, right? So that 4 neurons are there. So in a first iteration, batch 1 takes, the second iteration in the second batch 2 takes, and the next batch the data will be taken from batch 3. So in 3 iterations, these batch information will be fed to the input layer to process the final output. So if you observe here, the batch contains 4 values. Every batch contains 4 values. That's why in the input layer, I'm trying to take 4 neurons. So the weight matrix contains 3 weight vectors. So that I'm trying to take 3 neurons, which represents neuron 1, neuron 2, neuron 3. So that in the hidden layer, the size of neurons are 3. H1 represents hidden 1 neuron, H2 represents hidden 2 neuron, H3 represents hidden 3 neuron. So this is a big complicated complex architecture will be simplified in the form of input layer and the group of hidden layers or sequence of hidden layers. So if you observe here, this blue color and the batch representation are hidden from the hidden by your numpy. The final architecture will contains only the number of neurons in the input layer and the number of neurons in the hidden layer. If you connect every neuron from the input layer to every neuron in the next layers, nothing but hidden layer, this also look like a fully connected layer. So this is the final architecture in a simplified way to represent artificial neural network for this case number 6, which contains the batches of data from the input layer, how to process it through hidden layer. Now, case number 7. So here we are adding some more layers. If you observe, input also batches of data. These batches of data will be applied on weights 1, along with that bias. So the result of hidden 1 will be given to the next hidden layers. Here we have to take 2 hidden layers. So first hidden layer will take the data from inputs, it will process it. So the output of hidden 1 will be applied on the weights 2 matrix along with bias, so that your model will get the final output values. So here if you observe the vectorization representation, so for every hidden layer I have to produce the output. So first hidden layer, I'm trying to take a variable called layer1 underscore output, which contains the dot method with a numpy in a form of 2 parameters. First one is input 2 weights dot t, nothing but transpose plus bias 1. So after getting the output of this hidden 1, this output of layer underscore output will be taken by your next layers along with weights 2 dot transpose will be added with bias 2, so that you will get the final answer. So let us go for the tracing. So initially you have to apply the transpose on weights 1 along with inputs. So this is the representation. Input dimension is 3 by 4. So after applying the transpose, your weight 1 matrix dimension is 4 by 3. So that the dot product on 3 by 4 and 4 by 3 is possible, so that the output dimension is 3 by 3. Yes, likewise. So after applying the dot on inputs with dimension 3 by 4 and weights on 4 by 3, this is the final output matrix, which the dimension of 3 by 3 will be added with the bias 1, which contains data 2.0, 3.0 and 0.4. So if you sum this final answer, weighted sum plus bias, this is going to be the final answer of layer underscore layer 1 underscore output, like this. So now this data will be given to the next layers along with weights 2 dot transpose. Now this output, I'm calling it as layer 1 underscore output. So now let us discuss about how to apply weighted sum on layer 1 underscore output with weights 2 transpose. So this is the answer of layer 1 underscore output. After applying the transpose on weights 2 matrix, so here this is the final answer. So on that you are applying a weighted sum. This is the final answer. So on this final answer you are adding the bias 2. So this is going to be the final answer with a dimension of 3 by 3 given by your model, which represents this is the scratch program type manual tracing. So the final output will be stored in the layer 2 underscore output. So if we observe the previous architecture, this previous architecture is almost similar, nothing but similar to our inputs into weights 1 dot transport, so that every batch will have 4 values. So 3 batches are there, and this will be mapped with the weight vector with the dimension of 4 by 3. So that neuron will get 3 batches on first column vector, 3 batches with here for second neuron, 3 batches with second column vector, and for the third neuron 3 batches with third column vector. So on this you will get the output as layer 1 underscore output. So this output is given to the weights 2 dot transpose, so that the final answer will be 3 by 3, look like this. So up to here we completed the batch 1, batch 2 data, batch 3 data mapped with neuron 1, neuron 2, neuron 3, and I'm calling the next layer of neurons as neuron 4, neuron 5, neuron 6. The output of this n1, n2, n3 is 3 by 3 dimension. The output of the dimension of this weights 2 dot transpose also 3 by 3. So 3 by 3 with 3 by 3, the multiplication will happen properly, so that 9 combinations will come. So if you observe, the next layers also fully connected. Every neuron from the first hidden layer is connected to the every neuron in the next hidden layers. So that n1 is mapped with n4, 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 n5, n6, n2 also mapped with n2, n4, n5, n6, n3 also mapped with n4, n5, n6. So that the final output will be batch 4. Why batch 4? The output, the layer 1 underscore output, I'm calling it as batch 4, batch 5, batch 6. So it will be applied on every vector from the weight 2 dot t transpose. So that I'm calling every column vector of that weight 2 dot transpose 3 by 3 dimension as weight 3, weight 5, and weight 6. So that if you observe, if you convert this one into a artificial neural network category, so this is the model of it. So the batch, 3 batches are there. Every batch will have 4 values. That's why I'm trying to take 4 neurons in the input layer, and this is mapped with 3 neurons in the first hidden layer, and here the notation is h11, h12, h13, nothing but h11, nothing but first neuron in the first hidden layer, h12 is nothing but second neuron in the first hidden layer, and h13 represents third neuron in the first hidden layer. So let us going further in the under coming to the next coming hidden layers. You need extra 3 neurons, which is labeled as h21, 22, 23, because the dimension is 3 by 3. So h21 represents first neuron in the second hidden layer, h22 represents second neuron in the second hidden layer, h23 represents the third neuron in the second hidden layer. So if you ignore the background implementation by the NumPy, so my artificial neural network will look like this. Input layer contains 4 neurons, hidden layer 1 contains 3 neurons, hidden 2 layer also contains 3 neurons. If you connect every neuron which is available in the current layer to the next layers, nothing but every neuron from input layer to hidden 1, every neuron from hidden 1 to hidden 2, so that a network becomes a fully connected neural network. So as of now, we have seen how to construct a coding of neurons in different case studies with vectorization, without vectorization. So in the coming classes, we will see what are the types of activation functions which represents the second part of the artificial neuron, so that we can identify how the non-linearity can be achieved through artificial neural networks. So if you have any doubts in this session, please submit your feedback through this link. Thank you so much.